We can begin. I'm delighted to introduce Danika Van Niel to talk about equivariant structures witnessed by transfer systems.
Hi, everyone. Good afternoon. This is joint work. I'll talk about lots of different joint works. If you want my slides, they're on my website. So the link brings you to my website because I was like, oh, I'll update my slides, and then I never did. So it'll be a little bit different what you see. So it's with Kristen Mazur and Helico Sarno, and Sansa Roytime, Breakus Sandano, and Valentina Zapata Castro. So our first project that we did together is what I'll be focusing on, and here's the archive link. I also, at the end, will talk about joint work with Sarah Planerman, Chloe Lewis, Harley Monson, and Koki Shibata. That's pretty cool. These two are undergrads of Chloe Lewis's, so I think that's really cool. And then I also mentioned joint work of people whose first name I did not put, but David DeMarc, Michael Yagil Camel, Nelson Nino, and Kurt Stockel, and Goki Young. Okay, now that I got all the names out of the way. Let's do some motivation. You know, as everybody's been saying, hopefully we're all kind of motivated about equivariant things, because I'm going to use more equivariant things to motivate the stuff I'm going to talk about. So, G's and bar functors, which thankfully Mike defined for us today. These, you could think of them as an equivariant analog to commutative rings. And here C6, you know, C6 is an approachable group, and already it looks kind of crazy, right? Because we need a commutative ring for every level G mod H. And then we have all these arrows, right? So my restriction is always going to be my left one, it's black and it's laying down. And then I have, which needs to be a ring map. And then I have an additive transfer, which is always in the middle, and it's green. And I have a multiplicative norm, which is pink or red or whatever that is, and on the right-hand side. Okay. So pretty complicated, as we saw today. There's all these TNR relations that we need to satisfy. Everything needs to be equivariant, yada, yada, yada. So these things can be really hard to even define. Well, we love generalizing things, and like Mike talked about today, Mike Hill and Andrew Blumberg, I guess it is anti-alphabetical, define what bi and complete G and bar functors are. And these are even more general things, right? And so here's an example of one. Well, I'm not really telling you what every level is, but you see that I've erased some of my additive transfers and quite a few of my multiplicative norms. All the restrictions always have to be there. It's like a different story. But you can't just go erasing willy-nilly. There's all these different rules and stuff that you have to follow. And like Mike talked about today, like him and Andrew found out that there's a way to do this with G transfer systems. And so now all of a sudden I can draw you two G transfer systems, and yes, the colors are on purpose and everything. And this actually is so much easier to look at, right? Because now I just have vertices. I don't have like these commutative rings, and then I need to define what all these maps are. Now I just have edges, just have directed edges. And so compatible pairs of G transfer systems helps us to know more about the additive and multiplicative structure of possible bi and complete and bar functors. Okay. So hopefully you're motivated. No, I am. More examples are ring G spectra. So this is so my projects with DeMarc, Hill, Camel, New, Stockel, and Jan. We're thinking about these things. Model structures, my WIT group, we're thinking about this as our second project. Operads, don't have a project on that yet, I guess. And then I'm sure that there's plenty more. Like, I don't know. To me, this stuff just seems so cool, and it's like so basic in such a nice way. And we found that it touches so many of our stuff that we think about that I feel like if we show this, I mean, maybe other fields of math already know this stuff. I barely know what they work on. But like if we show this to other fields, like I wonder if they're like, oh, we also have things like this, like that would be really cool for our work, you know, or something. I think that there's probably many, many more examples. Oh, okay. My G is always going to be finite and abelian until the very end. So I'm gonna define the G transfer system, but more so with drawings than maybe we've seen today. So G transfer system T is just some partial order relation on a set of subgroups of G represented by directed edges. So I'm about to show you a bunch of different conditions, but my running example, I'm gonna use G equals CP squared Q. For your favorite distinct Q's. So, primes, of course. So I have all these conditions, right? So first, the subgroup one, if I have an edge from H to K, then that means that H has to be a subgroup of K. Oh, sorry, I said that reverse. K has to be a subgroup of H. Reflexivity, I always need the map that goes from H to itself for all the subgroups of G. And then we get to transitivity. Transitivity really is just composition, right? So if I have something that looks like this, and I have the edge from E to CP and then to CP squared, I want the edge from E to CP squared, right? That seems like a nice to that's fine. So now this is a transfer system, this was not. And then restriction, things get even more complicated. So if I have some edge, and so Mike was talking about this actually a lot today. So if I have some edge from K to H and just some subgroup of G, I also need the restriction of these two subgroups. I need that edge to also be in it. So here I've started with an edge from CQ to CPQ. I can restrict by a lot of things. I can restrict by the whole group, but I just get the same edge back, so who cares? I restrict by E, but then I just get the edge from E to E. I already have that, who cares? Oh, also, I'm never gonna draw those, right? The ones that just go from themselves to themselves. But I do get something interesting if I restrict by CP, right? Because if I restrict CPQ by CP, I get CP. And if I restrict CQ and by CP, they have nothing in common, right? So I just go to E, the identity in common. So now this is a transfer system, okay? But even on the grid, there's all kinds of different things you could do. You have the vertical edge. So you could restrict by the other characters in line with you. You could have a diagonal one, right? And so then you sort of go punk, right? So you just like, you get these, it's almost like projections. That's why I really like the grid. The grid's really nice and it's nice to sort of play around with. So this is one way to define transfer systems, but if you're anything like me, I learn a lot from examples. So these examples are for general G's, well, finite G's, I should say. But my specific examples I'm going to show you are the CP squared Q. I'm just going to not label the vertices anymore. So you have the complete transfer system that just has all possible edges. And then Sophia set me up to this one. Thank you so much. This is a saturated transfer system. So a saturated transfer system is just one that satisfies this rule. Okay. So if I have some edge from L to K, from L to H, then I also need this edge from K to H. So like Sophia showed us, like you have the half smiley face, love that name, thank you.
Yeah.
You have like those bouquet kind of things, like the triangles. We'll go through examples. So let's take this one. We've already sort of talked about this character a bit. So if I focus in on this triangle, right, I can label my subgroups LKH, and now it looks like my character. So if I want to force this thing to be saturated, I need to add this edge. And then similarly, for this other triangle, right, I would need to add this edge. And then I've got the half smiley face, which Sophia already taught us about. And so I need to add that one, right? But now I have no other saturation failures. So we're happy. And so it'd be nice if this had a name. It does have a name. It's called taking the hull of a transfer system, T. So there's two ways that you can obtain the hull. They're equivalent. You could take the intersection of all saturated transfer systems which contain your transfer system, or you could do the saturation process that I just talked about. You can find all the saturation failures and just add in the edges that you need, and then make sure that it's still. So this is called the hull of the transfer system. Yes.
Is there any way to tell whether or not like adding some some maps to make it more saturated or to get there, will actually do transfers.
Yes, yeah, we do have approved. It's kind of the idea is that a lot of them are just gonna look like this, you know, where you already have, like, if you have a bouquet, right, and you add this one, you're not gonna be missing this one because you would have gotten it from the diag and stuff. That's sort of the vibey reasoning. Like composition and stuff like this won't force you to fail anything. But how about like the hull of something like this, where this is just generated by the big edge, right? What happens? Well, it turns out you get the whole thing. And so this is actually true about any connected transfer system. And so you could think of transfer systems as having connected components, which is it's defined probably the way that you're hoping it's defined, which is two vertices are the same connected component. If you can trace from one to the other in an undirected way. Okay, well, I've been sort of teasing compatible pairs and we've been talking about them throughout all of today. A pair of G transfer systems, T1 and T2 are compatible if, and I do apologize, this is the reverse order from how Mike talks about them. And I unfortunately do have my name on two different documents that use both ways. It's just one of the, one of those things. So here I want my first one to be smaller. I want T1 to be contained in T2. They can be equal. And then I have this compatibility diagram. And so this is what Mike was talking about today. And I realized when Mike was doing it that it was reversed. But from how I present it, but this is by David Chan. He's the one who figured this presentation out. So what this means is if these two edges are in T1 and this edge on the bottom here is in T2, then I have to have this edge in T2 in order for T1 and T2 to be compatible. Right, so it's an if-then statement. I do not expect you to digest that in one sitting or memorize it for sure. Although I guess you do for my slides maybe, but I'll keep bringing it up whenever we need to remember it. So let's talk about some examples. So you hand me some generic T and I hand you back the hull of T. Is this always a compatible thing? Is this a compatible pairing? Right, we're gonna play matchmaker, I guess. Well, T is definitely contained in the hull of T, right, by definition. And then if I look at my compatibility diagram, I can say, well, consider the case where B is actually equal to B intersects C, right? So I just shoot, and now I've sort of collapsed it into this straight line. And wait a minute, this looks like our saturation condition. Okay, so actually anybody that is, so not only is the hull compatible with T, but anybody that is compatible with T needs to contain the hull. Okay, how about the complete thing? Well, both of them are just factuously true. Of course, every transfer system is contained in its complete thing. And then the complete thing can't be missing edges, right? It has all possible edges. And somehow these are like the smallest pairing and the largest pairing. If you fix your smaller of the two, right? If you fix that one, this is the smallest pairing you possibly get, and this is the largest one. Right, so here's our example that we've been dragging through and we'll continue to drag through. So it's compatible with its hull, which we figured out before what the hull was, and it's compatible with the complete thing. So we called transfer systems which are only compatible with its hull and the complete thing, lesser simply paired, or LSP. Lesser meaning it's like the lesser of the two, like minor, major, other. And then simply paired meaning like it's only with the things that it has to be compatible with, right? So maybe let's think about some examples of this. Maybe we start with the one that we've been dragging through. Well, we already know it's compatible with these two, but are there others, right? There seems like there could be room for some. So, very suggestively, I'm going to say, why don't we add this green edge to the hull, right? So this is already a transfer system, which is nice. That's the first step you would have to do is like make sure it's actually a transfer system. And then you see, okay, is that thing actually compatible with T? And so this was a fun game that we played for a while before we started seeing some patterns. So in this compatibility diagram, this is supposed to be like a thought remembering bubble or something. The only interesting example of this is this edge that I added. Because everybody else, this is gonna be fine, right? Because it's the hull, it's saturated. So if I consider B intersects C and B, so B intersects C to be E, and B to be this, well, this is the whole group, right? So then if B is a subgroup of A, but B is the whole group, well then, oh, A has to be the whole group too, right? But if B is the whole group and B intersects C is E, then C has to be trivial. All right, I know you probably didn't agree to do a riddle today. But this actually makes the whole diagram collapse, right? Because now this is just a reflexive thing, this is a reflexive thing. So what does my diagram end up saying? The edge, if your thing has the edge from E to CP squared, then it has to have the edge from E to CP squared. Ding, 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 right? So if we fix our lesser of the pair to be this character up above, we do have somebody that is neither the hull nor the complete thing. And there actually are more, I can't remember how many more, of course, bored brain right now, but if you're looking for a fun activity or something that I would find fun, maybe you don't find it fun, you can try to find another one, you know? Okay. So a really easy example is when the hull of your thing is just the whole thing, right? Then there's no room to add edges, right? Your hull is already the whole thing. And so those are our one connected components or connected components. Okay, so any transfer system with one connected component. And so our group is there, Osorno, Reutzheim, Santana, and Zapata Castro. We said if T is any G transfer system, this is just assuming that G is finite. It's not even assuming that it's abelian. This is for any G transfer system. If T has exactly one connected component, then T is LSP. But sort of for maybe an uninteresting reason. So how about not so easy examples? Well, we could think about this thing. We just showed that this was not LSP, and now I have these boxes around them. It's not like Sophia's talk. We're not talking about weak factorization stuff, or weak equivalences. It's just these are the connected components. Okay. So, but then this one, so maybe you'd say, okay, well, by this one example, it has two connected components, not LSP. But if you consider this one, right, with these two connected components, any edge that you add in here, once you close it under being a transfer system, it actually becomes the entire transfer system, like the complete transfer system. So the only thing between here and the complete transfer system, well, there's nothing between here and the complete transfer system, is what I must say. So this is LSP, right? Because there's no other options. There's nothing to even compare, like see if they are compatible or not. Okay. So then the same group, we showed that if T is a CP to the R, Q to the S for R and S, at least one of them non-zero, a transfer system with exactly two components, then T is LSP if and only if one of the component is either the bottom row. And so here I'm keeping the same generic construction where this is E and this is the whole group, or symmetrically, it's the whole first column. Okay, but all the other ones are not LSP. So, all right, well, how about three components or more? Well, it turns out there's always a way, like a sneaky way that you could connect two of the components, but not even touch the third, right? And so what does that mean for us? Well, that means that there is somebody between the hull and the complete thing that you can be compatible with. And so then we also showed that, so if you have three or more connected components, then it's not an LSP. So, you know, throughout all of this, it feels like wouldn't it be nice if we had a list of all of these transfer systems and maybe in like order of containment? Right, maybe this could make things simpler, because you could say, okay, well, who is my hull contained in? And am I compatible with any of those? Right, and so, Jonathan Rubin, in detecting Steiner and linear isometry operads, typed up these amazing, I think in combinatorics they call it cascade diagrams. So here's the Klein 4 group, and so the yellow circles are their LSP for uninteresting reasons, because just their hull is the complete thing. And then the triangular green ones, those ones are LSP in an interesting way. And so here you can see there's lots of symmetry between these groups. So what this one is it's like he modded out the symmetry, right? So he's like, okay, this whole class of 3 can be represented by this one, you know, similarly for other ones. And in my other groups, we found these super helpful. I think other people have found these super helpful. Here's another one, here's Q8. And this one creates like what I feel is a very interesting pattern. Like all of a sudden we have all these interesting LSP characters over here, but it's like utilizing this Klein 4 looking thing on top. Right? And then we have Pac-Man. But yeah, we just have some interesting patterns, and you can study all kinds of different things with this. You could think about if things are saturated, if things are disk-like, which is co-saturated. So then we have this one, sigma 3. And so Vanderman, Lewis, Monson, Shibata, and I, we've been trying to do these for other groups, specifically not abelian groups. So here's A4. And something weird we found with A4 is that none of them are LSP in an interesting way. Like if you're LSP, that means that you are connected, right? We've also done a cyclic 3. We're hoping to do more, especially after Scott's code that he uploaded amazingly. I invited my undergrads to this, and I'm hoping one of them is willing to learn how to code C. It's been like a decade, I think, since I've coded C. But yeah, so we've made these like big Hesse diagrams, and we've not only just studied LSP stuff, we've also like labeled who's saturated, who's co-saturated, because I know some people have been interested in like enumerating these and seeing the ratio between saturated and co-saturated. And so we plan to publish this in the AMS proceedings. So if you have like examples or non-examples, or just interesting things that maybe you didn't plan on publishing, like in a journal, the AMS proceedings could be a really cool place for you to get your work out there. I know that's what we're gonna do with our drawings. So this QR code is to like a Google form that Kyle sent out, Kyle Ormsby, on Alice Chop a few weeks ago, I think. But yeah, so Kyle Ormsby, Constanza Right Time, and Scott Belcom are the 3 editors for this AMS proceeding. So if you have questions, you can ask them. I guess you could also ask me. I probably won't know as much, but yeah, thank you so much.
Said several times throughout the talk that it was loads of fun, and I totally agree that it looks very fun. However, I'm struggling to see the connection to the like equivariant homotopy. Like it does LSP, like, for example, LSP, but really my question stand for many of the combinatorial things you said. Does it say something that like the N infinity operad associated to is?
Yeah, so definitely, I'm definitely not an expert on N infinity operad stuff, but like, so if I, let me just do this. So, for example, for buying the Timbara functors, for example, if you say to yourself, okay, I definitely want this multiplicative structure. Right? LSP or just knowing what your compatible transfer systems are can tell you who your possibilities are for your additive transfers. Right, so like, because oftentimes, I don't know if you've ever worked with bar functors, let alone bicompletes and bar functors, they're just like really hard to like define sometimes. Like, because there's all these different rules that you need to follow and stuff, so just even having like this skeletal structure could, I think, theoretically be helpful, right? Especially if your multiplicative structure you want to work with is LSP, then you know that there's only two additive things that you can possibly do, and you don't have to like screw around with figuring out what else it could be. Because like you think about, if you are trying to think about some ginormous thing like CP to the RQ to the S, where R and S are huge or something, right? It could be really helpful to know, like, to not have to trace through all these different examples and try to see what's going on. In addition to this, like for our rangy spectra project that we're working on, like kind of the idea behind it is we're taking these little disk transfer systems or disk-like transfer systems which correspond to little disks, right? And we're trying to see, okay, what's the maximal additive structure that we can, oh, sorry, that's the additive structure, what's the maximal multiplicative structure that we could have inside of it? And so we actually use this idea of like saturation and stuff to prove that like, okay, if our additive structure is saturated, then that is our thing, right? Or like, it's kind of, it's not rolling off the tongue, right? But they do have connections to these other ideas, and like I said, I think, like I haven't even, like I haven't really studied myself personally their connection with Operads, but from our talks that we've seen, they seem extremely hard. So it's like, so if studying something that is so like digestible, right, could help with that, that seems pretty powerful.
What do you call this, like co-saturated?
Yeah, yeah. So, I'm not sure why we name anything. But, yeah, so co-saturated and disk-like, they just mean like that all of the edges you have are a restriction of some edge that went to the ultimate group, that went to the group G. Why is that co-saturated? I'm not sure, but maybe somebody else knows.
Like, you have saturated for transfer, then you have co-saturated for co-transfer or something like this.
Yeah, I think that must be why, yeah.
It's like mirror smile or.
Yeah, I guess, I haven't worked too much with co-transfer systems, but, yeah.
Any more questions? If not, we should thank Danika again.